In this video, we're going to continue our discussion on nomenclature and also talk about actually writing the formulas from the names in addition to getting the names from the formulas. So first off, to clarify something, and we've said this before, an ionic compound is basically a positive and a negative together. So positive ions and negative ions coming together. That bonding relationship is an ionic bonding relationship. Contrast that to if you have two nonmetals coming together. Those are not ions coming together, but they're actually sharing their electrons, so we call it covalent bonding. Ionic bonding, they are not sharing their electrons, so it's two ions, a positive ion and a negative ion, a cation and an anion coming together, and they're electrostatically attracted, kind of like two magnets being attracted to each other. A formula unit is the simplest representative particle of an ionic compound, so basically like NaCl. We're not going to say that's a molecule of NaCl, that's not correct. We would technically call that a formula unit of NaCl or sodium chloride. A formula unit is neutral, so the total positive charge must equal the total negative charge. So this is going to be useful when you're trying to figure out what is the formula when you're given the name. So for example, it would not be correct to say Na2Cl because we know that Na, sodium, is always a +1 ion, and chlorine as an ion called chloride is always a -1 ion. So if you were to have two sodiums and one chloride, then you're going to have a net charge of +1. And what this bullet point is saying is we can't have that. The formula unit is always neutral. So when we put these ions together, we're always aiming to create a neutral compound. So there's no overall net charge. If the ions in the ionic compound have the same charge, then it pretty much contains one of each ion. So for example, potassium and bromide, you only need one of each to create a neutral compound. A positive one from the potassium and a negative one from the bromine. One of each is all you need to form a neutral compound. With calcium and oxygen, both of them are 2, 2+, and 2-, respectively. So again, only one of each is required to form a neutral compound, the CaO, which we would call calcium oxide. If the charges are not equal, then we have to figure out how many of each are necessary to create a neutral compound. So first example, barium and chloride. Barium is 2+, we are going to require 2 of the chlorides in order to create a neutral compound, which is why it's BaCl2. 2 of the chlorines are required to form a neutral compound. And we're going to notice this is a subscript. So if you were to type this, for example, in your homework, don't write it as BaCl2 with a big 2. Try to write it as BaCl with a little 2. That's a subscript. So in Microsoft Word or in Google Docs, you can figure out how to do subscripts. And then just when you write it by hand, if you're doing your homework on paper, just make sure you write the 2 down below as a subscript. Next example, so lithium and sulfur. So the sulfur as an ion, sulfide, it's 2-. So since the lithium is only +1, we're going to require 2 lithium ions in order to create a neutral compound, lithium sulfide. So this is just kind of a trick, if you will, to verify that whatever chemical formula you came up with, is it correct? So kind of like the crisscross or crossover rule. So aluminum is always 3+, you need to memorize that. And oxygen is always 2-. You can figure that out from the column in the periodic table, but also something you should memorize. If you just take the 3 and the 2 and like crisscross them down, then you get Al2O3, and that works out nicely because the net charge, so for example, if aluminum is 3+ and there's 2 of them, then that's a net charge of, or that's a total positive charge of +6 for the aluminums. And if oxygen is 2- and there's 3 of them, then that's a total charge of -6 for the oxygens. +6 and -6 added together is 0, so you have a total net charge of 0. It's a neutral compound. But the quick way of just like checking is just the crisscross. So the 3 goes down for the oxygen and the 2 goes down over for the aluminum, and we can kind of quickly get the formulas that way. But again, this is like a shortcut. What's more important is to recognize why we needed 2 aluminums and why we needed 3 oxygens. It's so that we have the correct number of each ion in order to form a neutral compound. This cross-referencing is just kind of a shortcut method. Now for formula units containing polyatomic ions, so formula units, again, we're talking about ionic compounds where one of them happens to be a polyatomic ion. We're still following the same rules where we're trying to create a neutral compound. If the charges happen to be equal, we're only going to need one of each. So for example, the magnesium is 2 plus and SO4 2 minus, that is called sulfate. They both are a 2, so 2 plus and 2 minus, so we're only going to need one of each, so it's magnesium sulfate, just one magnesium, and one sulfate polyatomic ion. If the charges are not equal, then the total charge has to equal 0, so same as before. And one thing that we're going to do is we'll use parentheses if we need more than one of the polyatomic. So here's an example where we've got 2 polyatomics, and that's fine too. So NH4, and this is actually written incorrectly. I should fix this. It's NH. The 4 is a subscript and the plus is a superscript. But ammonium, NH4, and sulfate, SO4 2 minus. So because we've got a plus and a 2 minus, they're not the same. We have to think how many of one of them do we need to balance out with the other. So sulfate is 2 minus. So we asked how many ammoniums will we need to create a neutral compound. We would need 2 of them because this is only a 1 plus. So that's why there's a little 2 right here. So the NH4, that's your ammonium. And notice that we don't write the charge anymore. So once we put them in a compound, so it's like same thing with this 2 minus, we don't write the charge once it's written in a compound, in a formula unit rather. The NH4, this is ammonium. This little 2 here says there's 2 of them, and then this SO4, that's the sulfate. And then for the name itself, this is ammonium sulfate, but later slides will tell us how to actually get the name from it. In terms of just the formula, it's the same thing as before. You're trying to create a neutral compound. We would need 2 ammoniums and 1 sulfate to make a neutral compound when we put these 2 together, when we combine those 2. If an ionic compound contains a metal that can have more than one ionic charge, so basically like a transition metal where we are using the Roman numeral, then we have to figure out what the charge is on that ion. And the sum total, same thing, it has to equal 0. So we're still trying to make a neutral compound. So for example, they've got this Cr3N2 and the question says, what is the charge on the chromium? So what's the charge here? So thinking through, here, this is our thought process. The charge on the nitride, so that's the nitrogen, that's always 3 minus, and that's based on the column in the periodic table. So phosphorus and nitrogen, that column, that group, those are always 3 minus. And since there's 2 nitrogens, that means there's a total of -6 just for the nitrogens. Again, we're trying to make a neutral compound, so the chromiums have to total up to 6 positive. And there's 3 of them, so that means each chromium must be 2 plus. And then, why do we care that it's 2 plus? Because that's going to tell us how do we say and write the actual name. So there's the formula and the name. We are doing the formula and we'll do the names shortly. So now for actually naming the ionic compounds, there's 2 slightly different rules, but they go hand in hand. But we're going to drop the word ion when we start naming. So we're basically going to be combining the cation and anion names, but we're dropping the word ion. And we always do the cation first, so the positive one first, and then the negative one second. And this rule, positive first and then negative one second, that is true across the board. Whatever is positive or is generally more positive, and I know I'm kind of being vague here, that goes first. And whatever's negative or more electronegative, if we're talking about nonmetals, that goes second. So for example, MgO, we've got magnesium and oxygen. So it's magnesium ion and oxide ion. Now we drop the word ion and we just call it magnesium oxide. And there's no Roman numeral here in the middle because magnesium is always 2 plus. The purpose of the Roman numeral is to clarify what is the charge on the metal ion. But since magnesium is always 2+, there's no need to have a Roman numeral because it's just redundant. If you have magnesium in a compound, every good chemist knows it's going to be a 2+, so you don't need the Roman numeral. That's why there's no Roman numeral right here in the middle of the name. So this next example, HGS, common name is cinnabar, kind of looks like cinnamon. It happens to be an Hg2+, and since Hg, mercury, can have different charges, it can be a 1+ or a 2+, we need the Roman numerals, so that's why we have the Roman numerals in parentheses. So it's a mercury 2 ion and an S2, which is the sulfide ion, so we're going to call it mercury 2 sulfide, and that's how we would say it. That's how we would speak the name. Mercury 2 sulfide. Mercury 2 sulfide. And again, that Roman numeral is just clarifying what is the charge on the mercury, on the metal. So we can also get the formula from the name. We were just doing name from formula, now we're going to do formula from the name. So here's an example. It's iron 3 fluoride. So iron we know as Fe, fluoride we know as F, and the Roman numeral here tells us that the charge on the iron must be a 3+. Metals are always positive. We have a Roman numeral 3, so that means the charge is 3+. Now fluorine, being a halogen, is always 1-. So then you think, how many fluorines are going to be necessary to form a neutral compound with one of these iron 3s? Well, we would need 3 fluorines. So we should get Fe and then F with a subscript 3. So that's what they have here. Again, we're just combining the ions so that we get an overall 0 charge. The total charge must equal 0. Now, ternary ionic compounds are very similar. It's the same thing. We have the cation name coming first and then the anion name second. One thing that is different is if you're talking about a ternary ionic compound, that means one of them is a polyatomic ion. So we have our metal, and then this ClO2, that has an overall charge of 1-. So it is our anion. We still have a cation coupled with an anion, and it's still going to be the same trend, cation name first, anion name second, so which is potassium chloride. And then if the metal can have more than one charge, so when they say more than one oxidation state, that's the same thing as saying more than one charge. We're still going to use the Roman numerals. So here's CO, which is cobalt, and then ClO3, which is chlorate. Now, cobalt is a transition metal, and it's not one of those special ones that we said is always the same charge all the time. Now, in this one, they're saying it's a 3, and how do we know it's a 3? Well, ClO3, you make your flashcards, you're going to learn, you're going to memorize that that's always a 1-, and there's 3 of them in this formula. So if you've got a total of 3- from the chlorate, then that means the cobalt must be a 3+. So then the Roman numeral is clarifying the charge on the cobalt. So it's cobalt 3+, and then the chlorate is ClO3-, and then there's 3 of them. But anyway, that's how we got the name cobalt 3 chlorate. So next one, we've been talking about ionics, so all of these slides up until now is ionic nomenclature. The next set, when we're talking about molecules, so we have nonmetals and nonmetals, it's a new set of rules. So kind of, clear your brain. We're going to talk about a completely new set of rules specific to nonmetals bonded to nonmetals where we have covalent bonding. But binary molecular, so it's 2 nonmetals, the covalent bonding, and we're going to use the word molecule here. A molecule is the simplest representative particle. Before we had formula unit, now we call it molecule. And this slide, or this point, IUPAC has set the following order for writing the elements. This is basically just, these are roughly in order of electronegativity. So fluorine is the most electronegative element on the periodic table. That just means it's the most electron greedy. And then of this grouping, carbon is the least electronegative, but remember the rule where we said we write the cation first and the anion second. That's basically what we're saying here is, then they say the following order for writing the elements. So if we had, for example, carbon and oxygen written together, we're just saying that we're going to have the carbon first and the oxygen second. So that's why it's CO2, not O2C. So this is correct, this is not correct. Another example, if we had H and S together, the correct way to write it would be H2S, not SH2. So this would be correct, this would be incorrect. That's all it's saying, because this is roughly in order of electronegativity, so the one that's more electronegative just gets written last. That's all it's really saying. Kind of an ugly way of saying just go by electronegativity. Now, in terms of how we actually name them, so the first element in the compound is named first and the second one is named second, and the first element in the compound is going to keep its name. So we're not going to do any sort of name change for the first one. So for example, CO2, everyone knows that's carbon dioxide. So the carbon, C for carbon, and then the name carbon dioxide, we didn't do anything to the word carbon. We didn't change carbon to carbide or anything like that because it's first. But the second one, the oxygen, we're going to change it to oxide because it's the second one. So the second element gets the IDE ending. And then the di comes from the fact that there's two of them. But the point is that the first element in the formula is also the first one in the name, and you don't do any sort of name change. You don't do the IDE ending for whatever's listed first, but you do the IDE ending for whatever's listed second. So oxygen in this case. Oxygen became oxide. And then the di, again, there were two of them. So if you have multiple atoms in there, then you're going to use this Greek prefix. So mono, di, tri, tetra, penta. With this bullet point, honestly, I've never seen this, enea. But then we've got hexa for 6, hepta for 7, octa for 8, nona for 9, deca for 10. Now, a lot of these you could probably figure out, like hexa as in hexagon. Everyone's probably heard of a hexagon at some point. Octagon, and then mono, di, tri, these you could probably figure out. But I suggest you make flashcards for these because you're going to need to memorize them. Another quick example of just kind of reviewing this one. So let's say we had CCl4. So the first element in the compound is named first. So the first element in the compound is carbon. So this would be, the name for this one would just start off as carbon. And the second element in the compound, chlorine, we're going to change that from chlorine to chloride. And then notice there's 4 chlorines, so we're going to use this tetra prefix. So it's carbon tetrachloride. Now, you may have noticed I've only got one of the carbon right here. So why am I not doing monocarbon tetrachloride? Well, there's actually an exception. So we're going to do this exception on this slide. But basically, we're not going to use the mono anytime the first element in the compound is just one of them. We're not going to use mono here. That's the exception. But let's do these two examples because I don't want to skip this slide. So what's the name of this molecular? So we've got P4S3. So P is phosphorus, S is sulfur. The phosphorus is going to get no name change, so that's why we just have the phosphorus here, but there's 4 of them. So we're going to use the tetra prefix. Sulfur is the second element in this compound, so sulfur is going to become sulfide, and there's 3 of them, so we're going to use tri. So tetraphosphorus trisulfide is the proper name for this. And then this is obviously a mistake here. I should go and edit these slides and fix it. This one that I just X'd out, this would be dinitrogen pentoxide, in case you were wondering. For this one, what is the name for P4S7? So again, P for phosphorus, so it's just phosphorus. 4 of them, we're going to do tetra. Sulfur becomes sulfide, and then 7 has the prefix hepta, so tetraphosphorus heptasulfide. Now for the exception that I just mentioned, there's one exception when you're using these Greek prefixes. If there's only one atom for the first element, we're basically not going to use the word mono. So it's not monocarbon monoxide, it's just carbon monoxide. It's not monocarbon dioxide, it's just carbon dioxide. This is an example. It's not monoxenon hexafluoride, it's just xenon hexafluoride. So we're just going to not use the mono if the first element has only one. If we have mono for the second one, we will use it. So like carbon monoxide, the mono is indeed being used there. So the next acid nomenclature, so we just went through ionic nomenclature, and then we went through molecular, where it's covalent compounds. Now we're going to do acids. So again, a binary acid, we just have the two elements, so like a hydrogen and a nonmetal. It always is going to begin with an H, and that's following the same trend here. So when we're on this slide, H comes before these other elements. So that's one reason why the H is first. But you always have an H and then a nonmetal. And honestly, the H is what makes it an acid. So the H, when it dissolves in water, and the AQ, which we'll learn in another video, basically stands for aqueous. But when you have this HCl dissolving in water, the H breaks off, and that's what makes the acid acidic. But for the naming, we're going to use hydro to represent the hydrogen, and then the element and ic acid. So here, for example, we have fluorine. So we have fluoric acid, and the full name is hydrofluoric acid. For HI, we have iodine. So it's hydroiodic acid. So hydro for the H, iodic for the iodine, and then the word acid because we're talking about an acid. HCl would be hydrochloric acid, and HBr would be hydrobromic acid. Now, ternary oxyacids, very similar, but now again we're talking about we've got three elements. So we've got hydrogen, and then oxygen, and then a nonmetal. So just slightly different naming. We're not going to use hydro anymore, but instead is we're taking the name of what this polyatomic ion was. So notice this is NO3. NO3, that looks just like the NO3 minus polyatomic ion. And it makes sense that it actually is the polyatomic ion because remember, hydrogen is +1. And if you were going to couple a single hydrogen and the nitrate, you would get one of each, which is exactly what we have in this formula. For naming it, going from a polyatomic ion name to the acid, we're basically taking the 8 ending, so this is nitrate. We're taking the 8 ending and changing it to ic acid. So instead of nitrate, it's called nitric acid. So nitrate, the ATE changed into ic acid. Nitrate becomes nitric acid. And then here's nitrite. So here it's the ITE ending instead of ATE. Here we get an OUS acid. So nitrite becomes nitrous acid. And there's one kind of learning tool or a trick that you can use to try and memorize this trend where you've got ITE becomes OUS and ATE becomes IC. So it's I ate organic apples despite being poisonous. So I ate organic apples despite being poisonous. And this is how it helps you. So I ate organic apples despite being poisonous. So ATE becomes the IC and ITE becomes the OUS. So that's just kind of like a little way that you can try and remember that trend. ATE polyatomic ions, when they become acids, where you're basically coupling it with a hydrogen, becomes ic acid, and then the ITE polyatomic ions, when you make it into an acid with a hydrogen, becomes OUS acid. So this is just a bunch of examples. So this trend where it's the 8 and the ITE, it goes a little bit further. So, and this instead of chlorine, this is the most common one, but we've got chloric acid and chlorous acid that came from chlorate and chlorite. We also have this perchlorate polyatomic ion, so ClO4 minus, that was on the slide where I said you have to memorize that. If that becomes an acid, it's the same thing. We're still taking the ATE ending and changing it to ic acid. So perchlorate becomes perchloric acid. And then I don't think, I gotta check if this one was on your slides, but ClO, this is ClO minus, polyatomic ion called hypochlorite. The IT ending still changes to OUS acid. So hypochlorite becomes hypochlorous acid. So just to kind of summarize what we talked about in this video and in the previous video, so we've been talking about nomenclature for inorganic compounds where they pretty much don't have carbon. There's a whole different set of rules for organic chemistry. By binary ionic, we mean a metal and a nonmetal. Ternary ionic means we have a metal and a polyatomic ion. And then binary molecular is basically we're talking about a covalent compound. And then acids, we can have binary acids or ternary acids where we have it's either hydrogen and a nonmetal or a hydrogen and a polyatomic ion. Cations, anytime we take a metal and turn it into an ion, we're just pretty much using the same element name and adding the word ion. Cations with more than one possible charge, so basically the transition metals for the most part, we're going to use Roman numerals, and the Roman numeral tells us the charge on the metal. Ionic compounds, when we're talking about the anion, we're using that IDE ending, so bromine becomes bromide, chlorine becomes chloride, etc. For ionic compounds, we use formula unit for the simplest representative. So like basically the formula is just called formula unit. For covalent compounds, we just call it a molecule. So the simplest representative unit for molecular compounds where it's covalent bonding, that's pretty much just called a molecule. This order is pretty much just based on electronegativity. F is the most electronegative in this group. Carbon and phosphorus, these are the least electronegative in this group, generally. The name for the first element is the same, and then ID is for the second. So if we're talking about naming molecular, where we've got two nonmetals, our example is like carbon dioxide, the name of the first element stays the same, and the second one changes to the ID ending. And then we're going to use those Greek prefixes, so mono, di, tri, etc. And then for acids, basically you take that molecule in aqueous solution. The hydrogen is what makes it an acid, and then that nonmetal can be a single element like chlorine or bromine, or it can be a polyatomic ion like nitrate or chlorate, etc. If it's just a binary, then it's hydro and then ic, like hydrochloric acid, hydrobromic acid, etc. And the ternary oxyacid, so we're basically just taking a polyatomic ion and coupling it with hydrogen, and then we're going to use that rule where 8 becomes ic and 8 becomes ous, and I just told you about the trick. I ate organic apples despite being poisonous. You can use that to remember this pattern.